Hello class, this is Professor Feynman. So now that we have done the explicit derivations of linear least squares, we're going to do two example problems. That way you can see and you can work along using either MATLAB or Python and perform the exact same regressions on the same data sets for the next two examples. And so we're going to illustrate both the simple linear model, and also we're going to do and then we're going to have another data set which we're going to try the different polynomial, just a general linear regression model. And so so let's do the simple linear model example first. And so we're going to use what's called a generated data set. We're going to use a known functional form. And so in this case, we're going to do y equals 1.5 times x. So the underlying function, okay, is a linear fit. And we're going to actually sample 5 points from this function. But we're also going to add, epsilon is going to be a random noise component, or white Gaussian noise. And so the epsilon will be normally distributed with a mean 0 and a variance of 0.1, or a standard deviation of 0.1. Remember, the standard deviation squared is the variance. So the standard deviation is 0.1. And if you're using Python or another scientific computing language, these will be our 5 data points. 0.9562, these are x and y variables. 0.9562, 0.5937, 0.2440, 0.6520, 0.2432, and then here are our y values. Now, how did I choose the x values for this example? I just randomly sampled x on a uniform distribution between 0 and 1. And how did I actually do the random sampling? I used our random number generator in MATLAB. And so this is actually, this block is a block of code from my MATLAB script I use to generate this input data. And so the first thing we do, remember, you turn on your computer and open up your MATLAB in this case, there's going to be a default seed number. So here, I'm just changing the seed number, and I'm using 890,231 for the seed number for this example problem. And so now here, the RNG, I'm setting it to the seed number. This is changing the seed number in the MATLAB random number to pseudo random number generator. And so the next, I'm just setting n equals to 5. That's our number of data points. And then STD is going to stand for standard deviation. I'm setting it to 0.1, corresponding to a variance of 0.01. And so I need my 5 xi data points. I'm setting xi equals 0, corresponding to, we're going to uniformly sample between 0 and 1, 0 plus 1 times rand. Remember, R-A-N-D, rand is the command in MATLAB it uniformly samples between 0 and 1. And then I'm going to make a column vector of n comma 1. So this gives me 5, n equals 5. So this gives me a column vector with 5 random numbers between 0 and 1. And that's what we got here. Of course, if we change the 0 and 1, then we can just do a uniform distribution on a different range of x. Step 2 is we want to calculate yi using this formula. Y equals 1.5 times x plus epsilon, our random noise. So I'm going to make a vector, build a column vector with our random noise. So I'm going to use EPS standing for epsilon. EPS equals 0. Now we want this to be white Gaussian noise, so the noise, the mean should be 0, okay, corresponding to here. So 0 plus STD, standard deviation, is set to 0.1 times rand n. That's the command in MATLAB it randomly samples from the the standard normal distribution. And so I'm taking, so the rand n rand n comma 1 gives me 5 random numbers from the standard normal distribution, but by multiplying it by 0.1, the standard deviation, we transform it into the normal distribution with variance 0.01. And so now I need to generate my y data points here in the second column. So it's y equals 1.5 times xi plus our random noise. And so now, you all should be writing your own script. You can either use MATLAB or Python, but you should, in this lecture, you should be following along, actually coding this yourself. If you're using Python, you can manually copy in these data points. I think Python uses a different random number generator, and I don't know what seed will give the exact same random number. So you can, if you're using Python, you can just manually transcribe this data into your Python script, and then you do the rest of the programming. And so what we want to do, now that we have our data set generated, we want to fit a simple linear model to this data using the sum of squares formula or using the explicit derivation. And so, we need to calculate the slope. So this is the explicit derivation, okay? Or you can calculate your sum of squares and then use the sum of squares formula. You should, for this first time, just do it both ways. You're going to get the same answer. And so then you can do your y-intercept. And so this should really take you about maybe 5 to 10 minutes. So you can pause the video and get this data loaded in electronic format. And calculate your beta 1 and beta naught. And then what we're going to do is we need to make a plot showing the data, the line of best fit using beta naught and beta 1. And also you should always plot your sample mean x bar and y bar on the plot. And we're also going to plot the underlying function y equals 1.5x. So pause the video and take 5 to 10 minutes to actually do this programming and make the plot. Okay, class, so now that you've restarted the video, you should have a plot that looks something like this. And so let's just go through. So the red dots are just the actual data points. Now this black dashed line, that's y equals 1.5x, are the exact underlying function. And the solid blue line is our line of best fit. And another thing, whenever you do a regression and you make a plot, like for example, if you're going to the conference, you're writing the journal paper, you always need to provide the actual, in this case it's just a line of best fit, you need to provide the actual regression function. Normally, you should do that actually in the legend, it should be on the actual plot. Now if it's a really complicated model with multivariate problem with many regression functions, there you might define it in the text of your journal article. But generally, if it's a low order polynomial fit, you should actually provide the actual regression, the final regression equation on the plot, like in the legend. And so, if you calculated your slope and y-intercept, you should have gotten 1.2167 for your slope, beta 1, and 0.20634 as the y-intercept. And then you always should plot the sample mean. Okay, so your mean of your x's and your mean of y, that's this black square. And so it's 0.5378 for the x bar and 0.86066 is y bar. And if you look, the mean point, the line of best fit, passes through the mean point. So here I've also calculated the x bar and y bar. It's just these 5 numbers divided by 5. I've also provided this, if you remember in the MATLAB code, we actually generated our epsilon, our random noise term. Here I'm just, these were the actual 5 epsilon values that the MATLAB, the pseudo-random number generator, generated for this example, using that random seed. and we're going to be using this particular data set for the rest of the rest of this online course. So this is why you need to get this information coded in either your Python or MATLAB. Because we're going to keep adding on, we're going to keep looking at other features of this data set in later course modules. One thing to notice about this data set, if you look at it, it's a small data set. The line of best fit, you see it passes between these 2 points, and also it passes between these two, and then there's 5 points, so it's, but if we look at the actual data set, remember we did random sampling of x between 0 and 1 following a uniform distribution. Look at data point 3 and 5. 0.2440, 0.2432. We happened in this particular example, these 2 data points have basically almost the same predictor value. Almost, I mean, we're talking the third significant digit. So it's essentially that's what happens with random number generators. I mean, it's not going to be like we happen to get 2 data points that were extremely close together. And let's look at the epsilon. Epsilon was supposed to be a random sample from the normal distribution with mean 0 and variance of 0.01 or standard deviation of 0.1. The 2 noise when we independently randomly sample these new noise components, the third data point has a 0.2083. So that's about plus from our normal distribution. It's that normal distribution with variance of 0.1. So that's a positive 2 sigma. The 0.20 is a positive 2 sigma. And so we're sort of sampling at one of the extreme, this epsilon term is a little bit of an outlier. It's sort of at the extreme, it's on the tail of the distribution. Also for the other data points, the noise is also positive sign and 0.1. So that's 1 standard deviation noise, 2 standard deviation noise, both with positive sign. Now this data point 4, the 0.6, and you see from the actual true underlying functions, these 2 data points, they have positive noise. So they're actually above the true underlying function. Let's see. This 0.59, it has a negative 0.07 noise, so that it's just a little bit below the exact function. And the other 0.65, it's 0.06, it's a little bit, its random noise component is near the mean of that distribution. And then our final data point is also negative, but really small, 0.03. So here, it's a little bit, the first data point is a little bit lower than our true function. And so in this particular data set, it's a small data set, 5 points. We have 1, 2, 3 data points with a positive noise component, and we have 2 data points with negative, where the random noise happens to be negative inside. But we have 2 data points that actually have kind of a relatively large noise component, and that positive noise components that have large magnitude the 2 data points almost have the same predictor value. And so, normally if you're doing a real experiment, you don't know what the actual noise component is, but this was a generated data set, so we can look at all of the components and how will that affect the fit. And so if we look at this, our exact function is y equals 1.5x. The slope, so this is the linear least squares fit, y equals 1.21. And also the y-intercept is 0.2. So the true y-intercept is 0. And so the first thing is the sample mean is slightly greater. It lies above the exact function, okay? But basically, we have 3 positive noise components, and the largest magnitude occurs near the left boundary, and it's both positive noise. So the line of best fit basically has to pass through these two data points, but these two data points are an overestimation of the true function. And so basically, we have our exact function. Because these two data points have this positive noise, it basically, you think of the mean point almost as the fulcrum of a lever. It has to, you have to decrease the slope in order, the least squares regression is basically decreasing the slope because of the positive noise in these two data points. And also, of course, with the decreased slope, when you extrapolate out to the y-axis, now you're going to have positive noise. If you put a negative sign on these two random noise components, these two data points would be shifted here. The slope would have to be increased, and then the y-intercept would be negative. But our linear least squares fit has we have correctly identified the slope is positive, but it's almost a 0.3 difference. So it's about a 20%. The slope is underestimated by about 20% relative to the true function that we were using to generate the samples. So there's just some things to look at for this data set. And so you should, if you haven't already, you should actually make this plot, because we're going to keep using this plot later on in other modules, okay? And so you should make this plot, and when you're writing journal papers, doing conferences, your actual regression equation, you need to actually include, whenever you show a plot with data and then a regression fit, you need to actually provide the equation. And ideally on the actual plot itself. And so now we're gonna do another really similar example, but this time we're doing the same. But we're gonna use the same underlying function with the random noise, but now we're gonna uniformly sample between 0 and 1. And so our xi's are now going to be evenly spaced. So 0, 0.25, 0.5, 0.75, 1. Okay, so we have evenly spaced data points, and I've generated another vector of five of these epsilons sampled from the normal distribution with 0.1 variance. And so once again, you can just transcribe this data. This is the actual, so the random noise component, if you need the actual random noise component, you can work it out from the equation, but here are basically our generated yi's. And so, once again, this is a small data set, only 5 points. And so once again, you gotta plot your mean point. But because these were evenly spaced, our mean is actually the midpoint of the range. The mean is 0.5 here, but the yi is 0.77844. And once again, our line of best fit passes through that mean point. And for this particular data set, our slope is 1.3443, y-intercept 0.1. And so that's just another simple linear model example, and you can put that into, you can also code these data points in your script. And so, so you should do these two examples just to gain some confidence with your plotting. And so now let's look at, we're going to use these, so we're going to always do two examples. One where we randomly sample the inputs, and then one where we use the uniformly distributed sample. And so now let's look at what happens when we add more data points. And so here I'm doing 25 data points. Once again, we're going to generate that data, and you can just modify your code to sample more data points, and you can repeat these. You don't need to do the exact same. I don't know if I'm using the same random number generator. You can try this many times. So first, So this is using the random sampling of X, and this is the uniform sampling on X. And so when we add more data points, our mean, I think our mean of Y, the true mean of Y is 0.75. So 0.5 and 0.75 are the true means of the function. And so here, the slope with more data points, the slope 1.43 and the y-intercept 0.005. We're starting to get a lot closer to the true underlying function we use to generate the data with. And also, we see a similar trend here, 1.4, 0.03. And that's also, all of these data sets are finite and relatively small. So so here, we would probably say that the uniform example here, 1.34 versus 1.2 compared to 1.5, we can't make any definite, we can't say that the uniform sampling is better. It just, it's a small data set with random noise. And so in the first example with 5 data points, the uniformly spaced example just happened to have a least squares solution that's closer to the true underlying function. But once again, it's a small data set with random noise. And so with the 25-point data set, the randomly sampled X values, its solution is a little bit closer to the true solution. So we shouldn't draw any conclusions about should we uniformly sample or do random sampling. That's not the point of this lecture. It's just from data set to data set, especially when they're finite data sets, you can get some large variations, okay? But here, the mean point is quite 0.5 and 0.742. So this mean point is almost the true mean of the X and Y. And so you should, so you can play around. You should generate many data sets with 25. You can just keep sampling sets of 25 random noise and redo these regressions and see. You can actually see the slope and y-intercepts. They'll vary. So you could repeat this many times. And so let's do one more example where we do 250 data points. Okay, so here we're showing 250 data points, and we really can't tell the difference. When we have this finite range and we have a lot of data points, you don't even know now whether it's random and uniform sampling just by looking at the scatter plot. And so here, the line of best fits 1.47, 0.009, 1.53, negative 0.01. So here, the slope is slightly overestimated, so our y-intercept becomes a negative by a very small amount. And so basically, these are about the same. And so as you add more data points, when you have data with noise, the more data points you have, I think in the limit that your number of data points go to infinity, your line of best fit will approach the true underlying function. Now in this case, we know we're using generated data. So in this case, we know what the true function is. And we're fitting a simple linear model. So our linear model, in this case, a simple linear model is the correct, it matches the underlying functional form. And the general experiment, you probably won't know what the underlying functional form is. And so, but if you do know what the underlying functional form is, if you do a lot of data points, even in the presence of noise, the linear least squares will converge asymptotically as the number of data points becomes large. And you can kind of see that here. So you could repeat this maybe with 5,000 data points. You're probably going to you're starting to get very close to 1.5x. And so, and so that's one thing. If you're going to do an experiment, the more that you can sample the input space, the more data, the better. And so whenever possible, you should try to increase the size of your data sets. But sometimes the experiments might be really expensive, or if you're doing the computer simulation, it might be a very long simulation. And so sometimes you're limited, but if you're not limited or constrained by the cost or the time it takes to generate the data, try to generate as much data as possible. That will make the regression, there's more you can be, doesn't make the regression better. You will be, the more data that you can provide to the regression, the more concrete conclusions or inferences you can draw from the regression and also from the statistical properties of the data set. So let's do one more example, but let's look at the effect of noise and the magnitude of noise on the regression. And so here I'm doing the same two cases, but now our random noise is normally distributed mean zero, but variance of 0.25. So that means the standard deviation is 0.5. So we've increased the noise standard deviation by a factor of 5. And by just looking at the scatter plots, you can see there's a lot more, spread in our data. And so now what we do, once again, is 250 data points. Now our least squares fit. 1.38 is our slope, 0.04 is y-intercept. Here, 1.69, negative 0.08. And so in the previous example, when your noise is a small magnitude relative to your actual output value, we start to get, we can converge onto the true solution rather quickly. But when the noise level is high, even with a lot of it, look how dense X goes from 0 to 1. We have 250 data points. We still can get, this is about, 15 to 20%. It's not really error, but discrepancy between the true underlying function and the fitted curve. That doesn't mean our regression is bad. It's an artifact of the random noise in this finite data set. And so the larger the noise, the more variation you will see in your regression model based on the actual data that you have. But once again, if you kept sampling, eventually your regression model would converge to the true solution. So that's just things to think about. Do I have noise in my data, and is it small magnitude, large magnitude? That will affect. And so that's, and then when you're interpreting your regression model, and usually we don't know the exact underlying function. And so in the presence of large noise and finite data, remember, like your regression model, you're going to have some regression equation, some equation. You should really interpret these equations as semi-quantitative. Okay, we do have a slope value. It is a positive slope. It's probably, and even with just looking at this data set, there's sort of a positive correlation. We can say that with some high confidence, this data has a positive correlation between X and Y, but should we assign significance when the slope is 1.3813? I'm only giving you these 4 significant digits because because in the previous examples, I want you to be able to check your code. Like you probably shouldn't even have maybe 2 significant digits, probably even just one significant digit is probably more appropriate. Like this 1.3813 has really little significance, because if you just did the same experiment with 250 other data points, you could actually get a significantly different slope. So you shouldn't, it's a semi-quantitative. We can probably conclude there's a positive correlation, but the actual numbers themselves don't have that much importance. So don't get too hung up on, oh, well, this one's 1.69, that one's 1.38. It's not important. and you shouldn't be using this exact number to try to, I would say maybe to make a prediction. It's not it gives you a number with all these significant digits, but it's the actual number itself isn't that meaningful, because if you repeat the experiment with different data, you're going to get a completely different slope.